Hello, good afternoon. Welcome to the stream. Very exciting stuff today, I hope. We have an interesting bug to fix, and we also get to start on the process of register allocation, which is a very interesting topic with some, I won't say complex, but complicated solutions. This is probably this will be the most principled thing we've done so far. But it's going to be, I think for me, reading through the first sections of this next chapter that cover register allocation, I learned a ton and it demystified a lot to me, because it felt like from the outside, it's like essentially a constraint solving problem. And to me, that was like, oh, well, there's going to be a lot of backtracking, trying some solutions, and that there's not always a perfect solution to the problem. And luckily, that's okay that there's not a perfect solution, because for x86, well, if you run out of registers that are available, you go to the stack. And this is the case in a lot of architectures. So, obviously we want things in registers if we can for efficiency. They don't have to leave the chip, or at worst they go into a cache and then get restored, when context switches happen and so forth. But for the, for this particular project, remember, we're doing this book, Essentials of Compilation. It's not a big deal to use the stack. So we'll use registers as much as we can, based on the algorithms that are designed to solve this problem. And then if we run out, we'll just put things on the stack, and that's just how it goes. But it is going to be probably, I guess that we will be lucky if we finish one pass today, because there's a lot of material to cover. But before we start doing that, I mentioned in the announcement not too long ago that we have an important issue. And I was a little bit embarrassed and nerding out that you see the issue was filed by the author of the book. So so we're gonna read through. Excuse me. We're gonna read through his language, or I'm sorry, his issue, and figure out how to solve that. And I think that it's important that we do this because hi Isaac, welcome to the stream. If we get too far down this road and we haven't fixed this problem, there will be like some non-determinism in our output, our compiler output. So essentially, let's read the issue and then I'll show the code that I think he's talking about. So he says, in remove complex operands, the order of bindings matters because LVAR is a language of side effects, in particular includes the read operation. This we know. So using dictionaries is problematic. I'm like, okay. So here's an example that produces incorrect output if the ordering changes. So you have add the negation of read and integer to read and integer. So if you gave 5 and 10 as the two inputs in order, this should produce 5. So he's saying essentially this inner read happens first. But if the order of bindings gets mixed up, it would produce -5, right? So if it evaluates this read first and then this read, you get -5. Okay. So so I think let's look at the code where that is happening. One other point of order here is that after the stream ended, I did some code reorganization. I was kind of noticing that the code we were writing was not following the conventions that the Gleam language wants in terms of how things are organized. So I made a new namespace, and it's just this EOC. So our compiler module became EOC, and then all of our other modules are nested under that namespace. And this will make sure that it doesn't pollute the global namespace. So you'll note that now we'll have EOC passes, and then all the passes, EOC langs, and all of the intermediate languages. And then if somebody happened to pull this in, or we pull in some other project that might have something like langs, we will not conflict with that one. So that was a minor change I did last week after the stream was over. Okay, so let's look at remove complex operands. Okay, so there was, we kind of gave the answer here. Well, we didn't exactly, but let's say you negate 10. You want to, in this other primary operation, 42 is atomic, right? And let's real quick look here. Remember that read is not an atomic operation, and none of these are as well. So I think if we introduce a let binding for read, or we have read inside one of these other operations, and so there needs to be a let binding, we need to make sure that they come out in the right order. So if we look at RCO atom, I think what we need to do here is, instead of returning a dictionary here, we need to return a list of tuples. Okay, and then we can just remove this dictionary from list there. Let's make sure that we remove the dictionary from list here. We could also use list key store and so forth, which is, if you're familiar with Erlang, you'll be familiar with that. So dictionaries don't have order. They, underneath the covers, there are maps in Erlang which don't have order, but lists have an order. So then the question becomes, this is atomic expressions. The question becomes, sorry, give me a moment. Okay, these are mutually recursive functions, this RCO exp and RCO atom. So in RCO exp, right, so this one does not return bindings. We only do bindings to turn things into atomic. So like variables are atomic, integers are atomic, lets and primitive expressions are not atomic. Okay, so really it comes down to this. And there's a question in my mind about what is the order. I guess it matters. Right. So this is building up where this is essentially the tail expression, right? So we know that if it goes into here, you're always going to be returning either an integer or variable. Right, because as that leftmost item in this return tuple. So if it's primitive, it's going to be, if it's an integer just in place, you don't have to do anything. If it's a variable, you're reusing that variable. If it's any other expression, you generate a variable and a binding. Okay, so here I think the question in my mind is what happens when we are coming back. Like we've gone down this route and okay, so it's actually simpler for negate. You're only going to have one binding here because these two branches don't generate new bindings except for the contained expression. So for that immediate contained expression. So that's easy for negate. It's actually the problem is these binary operators, right? That ordering matters. So negate, we can just do list. We need to import Gleam list instead of dict. So we can do list fold. And here it's going to be, this is going to be a pair. I was tempted to make a new module called alist. But let's look real quick and see if there's a standard lib. If there's a key fold. I don't think there is. No, so there's key filter, key find, key pop, and key set. And no, these operate on lists of tuples. So yeah, so this is going to be a little bit, I don't know if we can pattern match in the head there like that. You gonna let me do that? No. Okay, so we'll do pair, and we're going to say let's look at the Gleam, the language tour, tuples. Okay, so you can just use subscript indexing. So we can do, this is pair.0 and pair.1. Okay. So then we'll do that down here as well. This is where it gets interesting, I think. Now fold is a fold left. So what we want is if in the issue that Jeremy filed, we want the leftmost part to be evaluated first, depth first, right? Hi, Jeremy. Oh, I'm sorry, I'm having a nerd moment. Okay, so we want this one to be evaluated first. So we want the leftmost. Which means in this case we want not dict merge but list append, so that the bindings from B, which would be the rightmost operator, or the rightmost operand, comes second. And then we'll do list fold. And here we're going to do pair, and we'll just do the pair dot 0 and pair dot 1 again. And we basically need to do this, and I think we will do some copy paste. Oh well, that's the only two, except this needs to be plus. That had a bug there. Okay, so I think it would behoove us to make a test for this. Maybe we can use this example in our test. Let's look at the test we have already. This one is more straightforward. That one, yeah, we tested the no-op case. Let's do order of bindings test. And I don't know, it needs to be pub. Don't know what we're going to do here, but let me just copy this. Because we don't have a partial evaluator or an actual evaluator for the Elmarn-var right now. So I can't say, you know, let's make a read function that takes 5 and then takes 10, or emits 5 and emits 10, and then evaluate this. That would take a lot more work than what I want to do right now, because I do want to get into register allocation today. But let's go ahead and see if this will tell us, if we can figure out what the result should look like, just out of intuition. So yeah, this has no bindings yet. Right, because uniqueify comes first, but since there are no bindings, there's no lets in this program, we don't worry about uniqueify. And we're on the second phase. So I think we can just go with this program directly translated. Okay. And we'll do lvar dot prim, and we'll do plus, and then the left side is negate read, except this needs to be wrapped in primary or primitive expressions as well, because negate is not an expression by itself. And the read does as well. Okay. Okay, and then we need another lvar dot primary operation and lvar dot read. Okay. I think that looks correct. So we have a program, it has plus, and the two arguments are negate of read and read. So what should the Elmarn-var version be? So it's a program. So I would expect, we can just write it out in, I would expect this is a, let's see, there's some of the examples up here. Right, so I would expect that we get let temp dot one read. Okay, this is just my intuition. And oops, I need more parens there. Yeah, I think this is what it would do. Because read is not atomic, right? So it should create a binding for that. And then it's got to bind this operation. And then it would be plus. Oh, but this read, the second read also needs to be bound. So, right? Yes, an attempt.3, yeah. Except I need to make sure I got my parens right here. Okay, so then we would do plus temp.2 temp.3, right? Like I think this is what we would expect. Yeah. Okay, I probably don't have the correct number of parentheses there, but it's just a comment. Okay, so we have a program, and let's do let. That does return an expression. Okay, so we have a variable, so this will be temp.1. Excuse me. And then that is going to be, this needs to be an expression, so it needs to be a primitive operation read. Okay. And then we're going to have another let. And this is going to be temp.2. And this is going to be negate of variable temp.1. And that's going to take a let as well. You know, there's probably a better way for me to do this, but okay, and then we're at the final expression, which is we need a primitive operation, a plus, and that needs to be a var because plus takes atom atomics in this, and temp.2. Temp.3. Okay, what's wrong here? Oh, I need to wrap this in a primitive operation. Jeremy, I don't know if you have thought about this that much, but because your course is in Racket or in Python, but have folks used more strongly typed languages that force you to do some of this stuff in your course? Because like one of the compromises I made in satisfying the Gleam language was that this primitive operation is a wrapper rather than sort of a structure with an operator and any number of operands, because I wanted to make sure that for the individual operators we got the correct number of operands. I don't know if you had any thoughts on that, but let's go ahead and do our translation. So we're going to do remove complex operands and should equal P2. Okay, and let's run our test. Okay, so we got something wrong. Oh, there's no camel approach. Yeah, so the first time I encountered some of this, I saw Joe Pollitt's his course, and it's not exactly the same, but it does start from the bottom-up approach. Okay, go with the alternative. Yeah, interesting. Yeah, if there were variants, so like if like if this variant could be directly embedded here, I mean, I guess I could do that, but then you would lose the distinction that it's a primitive operation. So like you would have to know, oh well, negate is a primitive operation, so treat it specially in your branches and so forth. Yeah, read would directly be an expression. Yeah. Okay, what did we get wrong here? So this is what we wrote. So that the inner part is correct. It might just be the order of numbering things. No, see, we've got... No, I take that back. So we do 2 reads, but it looks like the one on the right is happening first, which is incorrect. So, so I think we have, you see temp 3, which is on the right, gets read first. So our ordering is incorrect in here. Why would that be the case? I mean, we can switch these folds for fold R or fold right, depending on what it is in Gleam. We can do fold right and see if that fixes it. That would be my... that key is way too close to my backspace. There, I did it again. Okay, fold right, please. And we'll see if that fixes it. The other thing that we could do is we could do, flip the order of append. That's still wrong. So there's something else wrong here. Let's see how this version with fold right is wrong. It still has lets embedded in here, so like that can't be correct. Like this is a let containing a let. The problem is the append, perhaps. What we could do instead of doing this append is we could fold over the A bindings and then fold over the B bindings. Although essentially the append should do that. Like the semantics of it. Yeah. I might be okay now. Let's see. Is maybe just my assumption incorrect? You mean with the fold right or with the... Let's see. Let's see. Time. Oh, wait. Okay, hold on. No, that's still incorrect. The nested lets are okay. Yeah. So I guess the question was the fold right is if that's what you were talking about. Sorry, there's a stream delay. Let me run that again and look at the contents of this and make sure it looks okay. So top level, we have temp 2, bound to yeah. So this is correct. It's just what we expected it to come out to be is incorrect, right? Because this read goes into the negation, which gets bound to temp 2, and then temp 3. Yeah, so we just have a, like, the tail of this is the same. The difference is that temp 2 is on the outside, and like, because this is not, in Elmonvar, the lets are allowed to be on the right-hand side. It's a later phase that removes that. I think it's the explicate control that pulls the lets out. So yeah. Okay. So I was expecting it to be more flat, like what happens when you comes out of explicate control. But monadic normal form. Yep. Okay. So really what we need to do here is we need to say this is temp 2 and this is temp 1, but temp 2 here, let me just rewrite it, I think. All right, so what we need is this contains the let for temp 1. And this let is on the outside. Let me see if I can do this. Okay. So this has read. Okay, and then it has a negate. Right. Okay. So we're putting that in temp 2. So that's the right hand side of the let. And then we need the tail expression. Okay, so I just like slightly misunderstood how it should come out. Let's adjust the comment up here to do this. This should be, this has let temp 1 read. Let's rewrite that. So this is let temp 2, which has a let in it, temp 1 read, and this has negate temp.1. And this has a let of temp.3. The extra parens always mess me up here. Of read. And then that has plus temp to temp.3. Okay, so that's what our final program would look like, which makes sense. Yeah, I was expecting the flattening of the lets, and it just doesn't happen at this phase. Okay, cool. So let's make a quick order of operations. Let's say fixed order of operations consistency. Thank you for coming today, Jeremy. Love it. Interpreters are good for testing because you don't have to write. Yeah. The challenge could also be that when you do an interpreter, you might get the right answer, but not detect that you gave it inputs that could produce the answer that are like computed the wrong way. So yeah, it's a good point though, and I think that it might. We did that on the first session or two for Elvar. Well, and it's funny, like when I did compiler's class with the Dragon book, like nearly 25 years ago, we only did front end of the compiler, of course, and it was basically like I think the professor was looking for, he had his own like secret input programs that he'd use to test your solution, and he was looking for very specific like error messages printed out and stuff like that. So like having that kind of black box is nice too. It can keep you honest, and if they're cleverly crafted enough, then you get get interesting results when something's slightly not right. Okay, so and remove complex operands. Closes number one. Let's say fixes. Okay. Thank you. All right. Time to go back to the book. So, I alluded to it at the beginning. Register allocation is a really interesting and deep area. And like the goal here is to get as many variables into unassigned registers as possible, because operations on them are going to be faster, right? By the way, there is one more bug from chapter 2 that I realized over the past week. I'm just going to go file it, and we can fix it later. And that's basically it. The x86 64 ISA requires stack frames to be multiples of 16 bytes, or at least the calling convention does. I don't know what the distinction is there, but we have a bug in the prelude and conclusion that just takes how much space is required. So like we could just do Gleam run here and have it print out our program, and you can see it's adding 32 or subtracting 32. That's fine, but like if we had a different number of variables, we might get 24 or something, which is incorrect. So we'll need to fix that at some point. Okay, so the thing that we're working on today for the rest of the time will be, in chapter 2 we did assign homes, which basically puts variables on the stack. So variables in your program become stack locations, and we want to make some of those be registers. So like, how do you determine what registers to put things in? That is the essence of this. Okay, so I'm going to read a little bit here, and maybe we'll type out some of these examples, or we'll pull them up on the web. It might be easier to pull them up on the web. Let's see. Over here, and we'll jump to the repo. I'm just going to read the tech. There's a PDF around here somewhere. Here we go. Let's just open that. That'll be easier than me, because I prefer here, open, please. I prefer the physical copy, but that's not helpful for you all in the stream. So let's see if we can get chapters. Can you show the table of contents? Yeah, here we go. Okay, so let's look at this example here. So this is a program, and after instruction selection, you get something that looks like x86 assembly, but you've got variables in it. Right, so this is that x86 var language. So calling conventions are important here. We do generate a main function, and there's also the the readint thing that is in the runtime file that we compile separately. Okay, so the calling convention is that some registers have to be saved by the caller, some have to be saved by the callee. What does that mean directly? It means that, like, if the caller has to save it, then these could be used by that function that you're calling. So you have to hold on to those if you care about their values. And the callee save registers, these are ones that you have to be, if you are the called function, right, you have to be concerned that these need to be, I think it's that these need to be restored when you're done, right? So it's the convention here is that the caller will hold on to these if it cares, and then you need to protect these or restore them when you're done. Okay, so right, let's keep going. Right, the caller should assume that all caller save registers get overwritten with arbitrary values by the callee. Right, so it's like a contract, right? You hold on to these, they'll hold on to those. Okay, the callee can use any of the caller save registers. So essentially, like when we're inside a function, we can freely use like, you know, REX, RCX, RDX, etc. However, if it wants to use one of these, it must arrange to put the original back in the register prior to returning the caller. So it would be like at the beginning of the routine, we might, anything that we use out of these, we would push onto the stack. And then at the end, we would pop them back off the stack into the original registers. Okay. Yeah, saving the value of the stack in the prelude and restoring the value in the conclusion. And then there's also registers used for passing arguments. So the first 6 arguments of a function are passed in these registers. Okay. So if we have functions that have something other than 0 arity, we might expect, you know, if it's an integer input argument, we would expect it in RDI, RSI, so forth. Okay, so, you know, readInt takes 0 arguments. It returns the value in RAX. Note that RAX is a caller saved. So, and that's largely because you expect the in this case, the return value of a function. Hi, Chris. Welcome to the stream. You expect the return value of a function to come in RAX. So yes, you need to hold on to that if you care about its previous value. Okay. Yeah, so let's figure 3.2 if we can get down. Where to go? Figure 3.2, is it up here? No, that's 3.1. I guess we'll have to scan ahead. We're getting okay. So here's 3.2, and I'll read along in the text at this point. Okay. So it says we first analyze this example from the caller point of view, and then from the callee point of view. We refer to a variable that is in use during a function call as a call live variable. And this is actually the first task that we're going to try to tackle is liveness analysis. And I don't have any idea how this is going to go because I read this earlier this week, but we'll see. Okay, so in this program, you're calling read and storing it in the value x and the variable x, right? And then you go on to the next expression. You call read again. You store it in y, and then you add x and y together, and then add 40 to them. And that's how that should work. So the generated assembly, as an example, is you call readInt, and then you put its its result into the register RBX. Remember, RBX is a callee save register, so this is safe to store things across functions that you call. Okay, so then it's calling readInt again, and then it's putting the result of readInt into RCX. And this RCX is a caller save register, but since we're no longer calling anything else, we don't need to save this separately on the stack. Okay, so now we have these two reads in RBX and RCX respectively. And then we add them together. That's this operation. And then we move the result into RAX, because RAX is going to be the return value of the function. And then we add 42 to it, and we jump to conclusion. So this is interesting. Maybe you can comment on that, Jeremy. I just filed that issue that they need to be multiples of 16 bytes. Is that incorrect? The stack frames. Anyway, okay. So that is kind of like what we're going for in this sort of 16-byte aligned is correct. So is it just that we've already pushed and then we subtract 8 to make sure that it's 16 bytes aligned? That's possible. Okay. Yes, okay. Got it. Okay. Let us keep going. Okay, we recommend an approach that covers. So the idea here is that we're going to. We jumped past into the liveness analysis section. Okay, so where does that interference graph get discussed first? Right, so what we need to do is we're going to create a graph that shows the conflicts between, the call to main push the return address. Thank you. Yeah, that's the other bit. Okay, so we're going to create a graph that shows and the example given here later is a Sudoku. Like you're trying to take into account the constraints of these two things can't exist at the same time in the same place. And this is the same sort of thing that think about lifetimes in Rust. Like it's tracking how long is this variable live, and do things that reference it escape that lifetime, right? Or are two flavors of lifetimes, like mutable or immutable, or rather borrowed or owned, or exclusive, are those active at the same time? And that's sort of what we're going to do here to allocate registers, is we're going to say we have these variables, they have these relationships between one another based on the operations they're involved in. And then we're going to create a graph that lets us figure out where we can place each variable into a register, and make sure that when that variable is no longer live, that register could be reused for a different variable, potentially. So that's what this interference graph thing is about, as I understand it. Okay, so during liveness analysis, we know which variables are call live because we compute which ones are in use at every instruction. So that's going to be our first task, is compute which variables are live at each instruction. And then you build the interference graph. We place an edge between each call live variable and the caller saved registers. So that means that I've got foggy there for a second on that. This is going to be, I've never done this before, so bear with me. Okay, so variables that are not call live, we prefer placing them in the caller save registers to leave more room for call live. Okay, so call live meaning that this variable needs to live across a function call, right? And if it's no longer live, then you can put them in a register that can be overwritten by the caller, or by the called function, right? Because you don't care about it anymore. Okay, that's the essence of this. All right, so figure 3.2 again. Let me get in the text here so I can see it. Okay. So in figure 3.2, we can do like by hand the analysis of the x86 code. And we see that, in this example, X is assigned to RBX. Which is a callee save register. Thus it is already in a safe place during the second call to read it. We talked about this a moment ago. Next, variable y is assigned to RCX, a caller saved register, because y is not call live. So y is not live until after this function call, right? After this call, y is not live until here. So it's safe to assign it to RCX because there's no other calls. Where'd we go? Okay, so that's from the caller point of view. From the callee point of view, if we look at the prelude and the conclusion, so the main function, so the prelude begins with saving the RBP register to the stack and setting RBP to the current stack pointer. Okay. So the reason we push RBP is because it is a callee save register and we're going to manipulate it. Okay, and then it pushes RBX because we use RBX in this function, right? So whatever value came into main in RBX, we need to restore at the end because we manipulate it, and it is a callee save register. So note that we're treating this from both we are calling things where we need to care about what the register, where the registers are saved, and we are also being called. So this main is called by the operating system, but it's still a function call, right? From the assembly point of view, it's still a, we need to observe these conventions. Okay, so we have to push RBX on there, and then we add we subtract the 8 from the stack pointer, essentially move it down another 8, so it's aligned. Okay, and then in the end, we are doing the inverse operations we did here. So we're moving the stack pointer up 8 bytes, and then we're popping RBX off the stack, and we're popping RBP off the stack. And then when we've done those, we know the stack pointer is also back where it was when we entered main, because pop subtracts or adds to the stack pointer. Push subtracts. Okay. So let's talk about liveness analysis. So what we want to do, this uncover live pass, in chapter 7 we'll be calling ourselves. Yeah, that'll be fun. Just out of curiosity, do you cover tail calls at all? That's an interesting tail call optimization, an interesting problem. Of course, cool. Of course you do. Excellent. I look forward to it. Okay, so it's probably going to be next year when we get to chapter 7, folks. At this rate. Okay, so this Uncover Live is going to be performing liveness analysis. So we're going to discover the variables that are in use in different regions of the program. And the definition here is that variable is live at a program point if its current value is used at some later point in the program. And the essence of this is, and I'm going to skip some of the details here, is that you work backwards from the end. So you start from the end. At the end, nothing is live except for maybe, I don't know if you count register rex, the return value, as live at that point. But it's not a variable. So at the end, no variables are live. The return value should be an rex, right? And all of the variables in your function fall out of scope. You can if you want. Okay. I don't know that it matters. We'll get down to it later here. So after 5, none of these variables A, B, or C are in scope anymore, and so none of them are live. And then we work our way backwards to the spots before each step. So let's continue down a little ways. And we're talking about sets, so we'll use probably one of Gleam's. I think it has a set. Let's see. Yeah, it has a set data structure, so we'll use this probably. And we can convert sets to lists and do union subtractions and all that. Yep, union, intersection, difference. Okay, so the locations that are live after instruction are its live after set. Locations are live before an instruction are its live before set. And this is like a chain of things. So the things that are live before an instruction are the things that are live after the previous instruction, right? Okay, so we know that, I mentioned this already, it's the empty set after the last instruction. So then you can kind of inductively work your way backwards. And that induction is that the before set is the after set subtracting the things that were written to, the locations that were written to, and unioning with the things that are read. So let's just do one step. We look at this example. Starting at 5, we know it's an empty set after. So we take, to get the before set, we take the after set, subtract things that are written to. There's C is written to. And since, the empty set minus the set containing C is the empty set, we have the empty set. And then we union that with the things that are read from. Well, we know that C is read from and written to in add Q, and B is read from. So the before set should be B and C. Hope I'm doing that correctly. Yep, here we go. So, yeah. And then you can keep going. So this be, L before 5 becomes L after line 4. And then you do the same for 4. You say, looking at this example again, scrolling up. So you're doing a move Q of 10 into B. So B is written to, you subtract that. And there's nothing read from. Is that correct? So it would only be C is live there. Okay. Okay, so maybe what we'll do real quick is we'll take this example. Let's see if I can copy paste it easily. Maybe. PDFs are weird. Okay, so we're going to make a new file here anyway. This is Uncover Live. So we might as well just start putting some comments in here. Okay, and we can remove the line numbers. I don't actually care about those. And we'll probably use this as a test case as well. So I'll go ahead and make a test file. Okay, we'll save that. All right, so we know, let's just create some columns here. I don't have, unfortunately, org mode to help me out with tables. But let's let's say this is the before, and this is the after set. Okay, maybe we'll do after and before. That'll be easier for our typing sake. Okay, so we know that after that there's nothing, it's the empty set, right? Before we have B and C because what we mentioned just a moment ago, B is read from and C is read from and written to. So these are both read from, and that's the set in the end. Here, so the after set, we propagate it backwards. So there's the after set for this step, this line. And the before set, so we know that B is written to, so we subtract it from BC, and then we don't read from B here, so we have just C. Just C is live before this. Okay, so C is live in the after set. We are writing to C, so we subtract it from that. Let me make sure I have this up correctly. So the before set for this step is you subtract the written to, and you union the read from. So the before set is actually just A, right? Because C is not read before this point, or not written to before this point, not read. Yeah, so the before set is A. And so then we'll continue propagating backwards. And we have B is written to, and nothing is read from. So subtracting B does nothing. And make sure that's completely on screen for you folks. And then nothing is read from. So the before set is just A again. And here the after set is A. So essentially we have a useless instruction here. This dies before it's overwritten, right? And the before set is nothing existed, right? Because we're writing to A and nothing is read from. So this is the empty set. So that we've done our analysis here of everything that's live before and after. Of course, we're after and before. We're doing it backwards for every statement here. Okay. Let's see. There's a special case for jump instructions. The locations that are live before jump should be the locations in before at the target of the jump. Yeah. So, so we need to keep a record of label and live that matches each label to the L before for the first instruction in its block. Okay. For now, the only jump in x86 var program is the jump to the conclusion. Okay, and the conclusion reads from RAX and RSP, so the A list should map conclusion to the... We could, as long as the order doesn't matter for this one, which I don't think it does. It does for the instructions, but not for the labels. We can probably just use a dictionary again. Okay, so yeah, label is fine. Thank you, Jeremy. Okay, so we did the perform liveness by hand on this. Okay, and there's figure 3.5. So let's make sure we got that correct. And I'm going to have to shrink this a little bit. Okay, so before is BC, after is empty set. Before is C, after is BC. Before is A, after is C, A and A, and empty set in A. Yep. So, okay, so here's another example. If we ran the liveness analysis on this, you can see there's actually variables and registers in here. All right, let's go back. Okay, so we're going to try to implement this pass. Okay, and we need to make sure that the block, yeah, so it needs to have an info field in x86 var. So I think returns the list. Oh, okay, so we recommend creating an auxiliary function that takes a list of instructions and an initial live after set, typically empty, and returns the list of live after sets. Okay, so we're gonna add info on this, and this is gonna break a bunch of stuff. So we're gonna say, and I think that okay, let me finish reading this exercise. Recommend creating auxiliary functions to compute the set of locations that appear in an argument. Compute the locations read by an instruction, so the R, and the locations written by an instruction, the W. The call queue instruction should include all the call or save registers in its write set, W, because the calling convention says that those registers may be written to during the function call. Likewise, the call queue instruction should include the appropriate argument passing registers in its read set, depending on the arity of the function called. So that's why we have the call queue has an arity, right? Okay, so let's, let's defer changing that structure, and I think what we want to do is do these computations and then see what we want to put into the block info field. Okay, so let's make a function that is locations in argument, right? And this we're going to import Gleam set. No, too eager. Sometimes. There we go. Okay. So this is going to, we probably need to define locations. And I think, I'm not sure whether we'll put that here. I remember a while back where I felt like var should be its own structure. It's starting to feel like that. But let's make a type location, and we're gonna import x86 var. This is going to be a register. There's an x86 register. Or it's going to be a var string. And reg. Okay. So what we want this to return, so this is going to take this type, right? So arg is x86 var arg. And it's going to return a set of location. To do in there. Yeah, never used. Okay. So, like we do so many functions here, let's just do all the patterns there. Okay, so for an immediate value, we just return a new set. There's nothing, that is in the binary. So if this is a register, then we want to do, we'll just do set from list, and we'll do the location, or rather register reg, right? So we know that this register is, we haven't, I don't know what to do on the deref. We'll figure that out. So this is a variable that has a name. Let's do set from list var name. So for deref, I think this, when we're in this phase, we shouldn't have any derefs yet because we haven't assigned homes. Let me look at assign homes, what we did. No, in assign homes, we chose to go from x86 var to x86 int. This uncover live is going to be var to var. The thing is, I don't know that we will ever be before this phase. I don't know that we'll ever be using a deref for anything. Like, I don't think we generate it. Let's try a little thing. I'm going to comment out this variant and see what breaks. Well, of course, matches. That's all in assign homes. Because I think essentially we're going to replace assign homes, right? Because it was a very naive version of just put every variable on the stack, right? So I think like let's look at this assign. Right, so this produces the deref, but it produces it in the x86 int language, not the x86 var language. And that would be the only place where we would create derefs. So I think honestly, yeah. Yay, type-directed refactoring. We don't need to handle this because it doesn't exist. I mean, I'll leave the variant in there commented out, right? In case we need to resurrect it later. But we should not be generating any stack locations at this point. Like, we will as we assign things, but I guess the other possibility is that I don't know if the graph coloring algorithm and all that will need intermediate steps where we have something else in x86 var, but now it has stack locations in it. Pointers. But I think that this is, yeah, I think this is it. So we'll comment that out for now. Maybe we'll resurrect it later if we need it. Okay, so we've got one that takes an argument and produces the set of locations, right? So variable or a register. Compute the locations read by an instruction. This one will be fun. An instruction. And this is going to be 6 var dot instruction inster. It's not happy about that for whatever reason. Okay, so this is going to produce a set. So this is a read set. And then we'll have a write set. Okay, so let's look at instruction. So so the read locations for add queue are, so the union of locations in arg for A and locations in arg for B, right? Because you both read from B and write to it. And then for this, yeah. Okay, so here's where some of that text comes into play. Let's actually move, I want to move these to the bottom. We'll deal with them later because the other ones are easier to understand. Okay, so this is locations in arg of A. Right, because you don't care about what's in the right-hand side of this. You're not reading from that, you're just writing to it. And this is going to be the same. Okay, and this one's going to be interesting. So this is, you're writing to A. So honestly here, this is a register of, you're also writing to, but that's RSP. Yeah, because you're popping out of RSP, the stack. Yeah, I think that's correct. Okay, and push, you're taking whatever is in that. That's what you're reading from. Okay, let's get sub queue up here because it's like add queue. This is A and B. Okay, so let's go back to the text briefly. Okay, so the call queue should include all the caller save registers in its write set. We're not dealing with the write set. Should include appropriate number of argument passing registers in its read set. So, so here's the arity, right? Maybe what we want to do, push queue also reads from RSP by the same logic as pop queue. Interesting. Why would that be the case? I mean, I believe you, but so let's do set union. Reads in the sense that RSP is pointing at a particular stack location and you're adding to that. Is that what you mean, Isaac? I mean, I'm okay with this. I think it, like, the intuition for me is that it's correct. Yeah. Yeah. Okay. So actually, it's more like you would think of it like a combination of two add queue instructions, right? So in this case, you're reading from B and A. So like if B here is actually, you know, RSP, right, or a sub queue rather would be more appropriate. You're like doing sub queue 8 RSP, and then like move queue of A into RSP, or the deref of RSP. Yeah. Okay. Cool. That makes a lot of sense, Isaac. Thank you for pointing that out. Yeah, it's a move queue and an add. Yeah. Okay, so we need. I wonder if I can do a. Let's do list dot take, and we need a list here. We're gonna do. Let's just go ahead and make the list because these are all the argument registers. Yeah, so it's going to be register of RDI, register of RSI, RDX, RCX, and R8, R9. Okay, so those are the registers for passing simple arguments. And then we're going to list take arity from it, and then we'll do set from list. Okay. So there is going to be a problem here that if the arity is greater than 6, then we need to use the stack, which could be an argument for the sake of we need deref, right? We might want to put a panic in here if arity is greater than 6. Yeah, that might be an issue to deal with. Okay, how are we doing? Okay, so let's go ahead and see if we can finish this and do write locations. So where were we? Okay, so there's some questions in my mind about I think it's up here. It talks about jump. Yeah, in chapter 7 we make sure it won't be greater than 6, and before then all the functions have smaller arity. Yeah, and honestly, you know, it might be good practice to not have too many arguments, but people will write whatever they want. Where was the thing about the jump instruction? Okay. Okay, let's go ahead and do the write sets. Yeah, I think read locations. RetQ would technically have RAX in the read, would it not? I'm just going to put it in there. And then jump. I don't think that this has any, because it doesn't change any registers except the program counter. So I think this is just an empty set. We may need to revisit that. And also the ret queue. Question. Okay. And I think I'll put them at the bottom of this case because these others I feel more confident about. Okay, so let's do the same for writes. All right, so we know here that this is, nope. This is locations in argb. Okay, so call queue, the write locations would be rex, right? Okay. Jump doesn't do any writes. And we're going to move this down to the bottom because, again, I'm not sure. Move queue moves into B. Neg queue is going to be that location. Come on. Okay, so pop queue is interesting in that it's going to do that plus RB or RSP, right? And push queue is going to be the same. Ret queue would not have any writes. Again, I'm going to move this down to the bottom and ask if that's correct. Okay, and then for sub queue, it's the same as add queue. Okay. So now we have, we have our auxiliary functions to compute the set of locations of parent arg, locations read and locations written. And so in order for us to do this uncover live pass, I think that we're going to need this to be public. What we want to probably operate on a block, but all of our passes so far have been full programs. And there's the... So let's take the program. And I think that we return another program in the same language. And what we'll do is we will have an inner, like, uncover. Where we, since we don't have the prelude and conclusion yet, we really only have one block, right? But I get the sense we might need to do this. Let's do it over a block. And then we'll revisit this. I think that there's a case to be made for, you know, we generate these, and then we have to do. We should be doing liveness analysis on them. Yeah, stepping over. Thank you, Jeremy. Thank you for coming and for filing the issue. And have a good weekend. Okay, so maybe we just assume that it's a program, and then if we run into problems later, we'll adjust. Okay, so we want to... Our goal here is to capture the entire list of before and after sets, right? But it would really just be the after sets, won't it? No. So like for every, it would be like the total number of instructions plus 1 sets. So you have a before and the after. Okay, let me get over here. Store this, oh, live after. Okay, so we only care about the live after. In the info field of the block structure. Okay. So what we're going to do is let's move this into x86 var. Right? This is going to be a little bit funky. And then we're going to do so all of these are we'll say type location register var. The problem, though, is that this conflicts. Let's rename it variable. That's a little bit confusing. Let's call it because you know the way that Gleam structures its types is that you know your constructors of each variance are essentially functions that produce the type, the parent type. It's like not that surprising. Okay, so we're going to change this to location register, location var, and let's replace register with location register, and we'll replace var. We're going to have to be careful about that one. Location var. Let's do... There's not that many places. It's just right here, I think. Okay, and this is just complaining about unused. Yeah. Okay, so we're going to add to the block. We're going to have we're just going to make a live after. And that's going to be a list of sets of locations. Right? And we need to import Gleam set. Be nice if my book wouldn't keep flipping. Okay. And let's just import set. That'll look nicer. Okay, so that's a list in order of the live after sets. So now any place where we generate x86 var we need to fix. So here, we'll just give it an empty list. This is where default would be nice, but we have that in Rust and not in Gleam. All right, reload. Okay, here we go. Sorry, it's still complaining. Expected 2 arguments, got 1. I think I need to reload Z. Fine. Let's look at the errors. Okay, here, will you not disappear before I can save? All right, it's just not cooperating. I don't know why that buffer is broken, but oh, yeah, that's correct. Okay. Okay, so now we've refactored that. Show me the warnings, please. Yeah, it's just saying not used, not used, not used, not used. Nothing interesting there. Okay, so let's go. We're going to take input dot body. And we're going to do map values. And that takes the dictionary as its first argument. And what we want to do is we're going to map a block to a block, basically. But we need to have a function that gives us, like, goes through the instructions and gives us the list of live afters. So so this is going to be map values does take the key, but we don't care about the key. So it's going to take a block, and let's do live after is we'll make an internal function called compute live after that takes block dot body, and then we're going to say block block dot body, because we're not modifying the body here, but we're going to have computed a new live after. So the result of this is, oh, I need to make sure that that's x86 var block, right? And we can probably just put this in there. Okay, so now it's complaining about I don't have Yeah, let's put that back, because actually what I want to do is go so we just need to make this compute live after. So this is going to take instructions is a list of instructions. And it's going to return a list of set of location, right? So that's what we did these auxiliary functions for in the first place. So I want to look at the list module real quick, because I think that we want to do something like sort of like fold right, but it's like map right. Map fold? No. We could do this by hand, which we might need to. But I think that we don't need to. We can just do fold right. Okay, so let's do list.fold right. That's going to take instructions, and we're going to start with the after set is the empty set for the last instruction, right? That's not strictly true because of the jump. We're going to probably need to handle that. The other way we could think of it is that the live after is RAX, right, the return value, RBP and RSP, because of what the prelude and conclusion do. Now that's something that we could do potentially here with jump, but I'm not positive. Let's look at their example here. Yeah, so they're saying RAX and RSP is the let's see, the live after set for add queue. Yeah, so notice RSP is live through this entire block. So I think technically jump conclusion, the live after is RAX and RSP, because there's nothing written to and there's nothing read from. So I think that we need to probably start this with the return value is going to be in RAX. RSP is going to be used potentially. Yeah. Okay, so we're going to start with location register, sorry. RAX and RSP. Okay, so that's going to be our initial set. And then our function is going to be doing the computing the read locations and the write locations, and then doing the set manipulation. Okay, so we've got in our fold right, we're given the accumulator first and then the item. So So this is the live after is the accumulator, and the item is the instruction. If we get the empty list, we should panic. Panic. Like it should literally not be possible. Let's call this next. But we're going to do, I mean, the other way we could do it is like list first. That returns a result though. We could do, yeah, actually let's do that. Let's do let okay next list dot first let assert, sorry, of live after. Okay, and then we're going to do, so whatever we get the there's a question in my mind about, like, do we skip over this one and just do the live after for all the previous ones? Nah. No, I think because, like, even though this is not aligned here, you know, RSP is live before this move queue. So I think we're going to have n+1 live after sets, which is fine. I don't see a problem with that. So we're computing the before set, honestly. We could just make this before set of next instruction, and then say live after, right? Because that's, and then we'll make another function here, which is the before set, which simplifies this. So this is a the after, and let's do after. Let's name them consistently. This is a set of locations, and we have instruction, which is x86 var dot instruction, and this is going to produce a set of locations. Okay, so now we do that this computation. So the before of this instruction is the after. So the after set, and we're going to get the set difference present in the first set but not in the second, right? And we're going to do, this is subtracting the right locations, right? And then we're going to union that with the read locations. And that's it. Maybe that didn't need to be its own function, but there it is. Okay, so I think what we need to do now is let's do a test, and I want to see that what we get when we do this example is what we see on the right. So we'll have an additional one down here. It'll be REX RSP, and then it'll be, you know, this, and then that, and so forth. Okay, so let's go ahead and write that test. And I think I'm going to have to split my view a little bit here. That's good. And then we'll wrap up for the day, I think. And then next time we'll focus on building the interference graph, which is super interesting, and that's where the magic happens, right? Okay, so we want to have Glee unit should, and this is going to be uncover live test. Okay, so we're going to let's make the program, and let's import x86 var let's just do that for now. Actually, we want and block. I kind of want to import everything. How do you do an import star in Gleam? Unqualified imports. Is there another? It's type checking. Let's see if there's any type imports. We've done that. We could Google it. Gleam language import all symbols. Everything. No, that's not what we want. How do I import a whole library in Gleam? No, okay, so you can do that. We'll just do that. We'll just import the things we need. For now, we'll start with this. Okay, and we're gonna need to construct it. We're gonna need Gleam dict. Pick from list, and this is gonna be start, and we're gonna need a block. So the block is going to have a list of instructions and an after set, and let's get those instructions written. See if I can get my windows aligned a bit better. Fourths. This is second fourth. And we'll hide the project panel. And this will be third fourth. I don't use those very often, so they don't have key combos for them. Okay, so we need move Q, and this is going to be immediate 1 of var v, and we're going to need move Q, add Q, neg Q, jump. And we're going to need immediate and var and register, and we're going to need rex. Okay, That should be enough to write this in the most terse form possible. Okay, and then we're going to move 42 into var w, and then we have a move q of var v into var x, and then we have add q of immediate 7 into var x, and we have move q of var x into var y. This is a completely inscrutable program, no idea what it's doing. Var x into var q. No. Sorry. Var x into var z. Sorry. I don't know where I came up with a q. Okay, and then it's add q of var w to var z. Move q of var y into var t. And then we're going to have neg q of var t. So I need to import that. Oh, I did. Then we can have move q of var z to register rax. And then we're going to add q var t to rax. And then we're going to have jump conclusion. Okay, so for this, what we want to see is, number one, the instructions are unchanged. So let's go ahead and write up our transformation check here. And this is going to be block. And the instructions are going to be unchanged, right? So what should this list look like? Let's first do that. So what we can do is we can do set from list. And we know that this is location register, so we're going to import that. Location register, location var. Okay. So we're just going to do, we're just going to go down the list here. So this is going to be, let's import RSP as well. Right? Okay, so this is going to be RSP. And then we're going to have a var location of v and RSP. I'm going to make this look as much like this example as I can. So we have, the next one is W and X and RSP. I'm going to flip those just so we're consistent. Oh, that was not the greatest. Okay, WX and RSP. Then we have that same set again. Oops. And then we have WXY and RSP. And then we have W, Y, and Z. Let's move that. And we have Y and Z. Remember, RSP is live through this entire thing. And then we have T and Z twice. And then we get RAX in there as well. So Z falls out. Yep, TZ RSP twice, RAX. T, and then RAX and RSP. And because we have, this is the initial, we have that twice. So they're not showing it here. Right, this is the before is the subtract the read from T and REX, add the written to. Is this just misaligned? Is that the issue? Let's think through this, and then we'll run our test and see what we get, and make sure that we're getting the correct thing. Right. So V is live after move Q because it is written to. Well, no, because it's read from later. So it's live because it's read from there, right? It's live across those three instructions, or rather those two instructions. It's live after this. It's not live before. Interestingly, I think our assumption here might be wrong. For let's save that. Oh yeah, I need to do the should. P to uncover live should equal P2. Oh wait, okay, so let's make sure. Like move Q, yeah, move Q doesn't consider the right hand side. It's like, where are you putting it? You don't care, you don't read from that. You're overriding that. Okay, so I was having a brain fart there for a second. All right, so let's, you're gonna make me restart Z again. How many updates do you need to do? Okay. So, yeah, let's run Gleam test. Okay, so it passed. So we got what we expected. The only difference from the diagram here is, or from the figure, is this additional one, which is our initial value. And that's fine because jump doesn't write or read from anything. At least not registers we care about allocating to. So I think that this is correct. Let's do one more example. Let's do this one. Let's call this 3.5. Let's do another one, which is, and I'm just going to copy and we'll modify, which is 3.4. Is the more simple one. And let's break this out. know that down here this is going to be instructions. Oh, too many brackets. There we go. Okay, so we're gonna change this up. We're gonna do this one. Except we're gonna have to make adjustments for it because this is, we include RAX and RSP in our initial set. We could technically I think we're just going to have to make adjustments for it. Or maybe it's even not that important because like this one is closer to reality. Yeah, let's just skip that. Let's not do that. Let me say figure 3.5 so we don't forget. Okay. We're not covering everything in our tests here. I think we kind of need an example. Maybe let's have something that from one of our other tests includes. Did I mess this one up? What did I do? What did I change here? Oh, it was like adding that. Okay. Let's, yeah, this select instructions might have something where we have read. Have any that have call queue? No. Does, oh, we don't have that, anything in there. This doesn't have any read instructions in it. Let's look for read in anywhere. Wow, it's not even in there. Okay. What were we doing on select instructions? And the passes. Why did it not find that? I was looking across the entire. Yeah, there it is. Okay, so here. Yeah, that's in the select instruction pass. Okay, so maybe let's just make an example. Yeah, let's just make an example of our own and do it as quickly as possible, and then we'll wrap up for the day. Uncover live with call queue test. Okay, so we're gonna say the instructions are, and we'll do the manual like thinking about what the sets are as we build this, and then we'll check our conclusions with the code that we wrote. So let's do let's import call queue. So we're going to do, say, call queue, and that takes read int, and then we're going to add queue of immediate 42 to register RAX, and then we're going to jump conclusion. This is a really dumb program, but it should be easy to figure out what the results should be. Okay, so we're going to start with basically this, and actually it's going to be the same there, right? Because we have the jump conclusion. And then we have, so let's think through add queue. So we know there's no locations here in immediate, but we're reading and writing to RAX. So writing to RAX, we subtract it from this, but we're reading from it as well, so we add it back. So the next one should be that. And then call queue should write to RAX but not read from it. So, oops, we're going to remove that. So it's just this. Okay, so let's say let p equals x86 program dict from list start, and we're gonna have block of instructions and the empty list, and let p2 is going to be basically here. P2 is going to be that, but it's going to be live after. And P has to uncover live should equal P2. And it helps if I actually make that correct. Okay. Let's run that test, see what we get. No failures. Okay, so I'm pretty convinced, we're doing the right thing under the assumption that this is the correct initial live after set for any block. And I don't know that we can reasonably make that assumption, but I think it's good enough for right now. And we'll go forth and next week learn some more. And I think I want to break this one out. It's too verbose. We'll learn some more, and then we'll if we need to revisit that assumption, we'll revisit that assumption. So okay. Let's do one quick refactor of this. We'll pull this out. Extract variable. Rename symbol. Will you do that for me? Oh, I need to do it. Oh, it's popping up here. Rename symbol. Live after. Okay. And then let's move this way up. Okay. And then these will be the instructions. Extract variable. Oh, perfect. And this will be instructions. Okay, now this one's a lot more compressed, and that feels better. Let's move the instructions up. Yeah, we could have done this as a list of tuples of instruction live after, but whatever. Unpacked it. Okay, let me make sure I didn't mess that up, and we'll make our commit. All right. So we've got all of that added. And this is chapter, we got up to 3.2. Build the uncover, well, we'll just call this uncover live pass. And then let's push. And there we have it. All right, next week we'll hopefully make sure that all of the stuff that we did was correct. Maybe we won't need to do too much there. But then we can start working on the interference graph and go through all those interesting diagrams that are in this chapter, talking about how you build the interference graph and determine what registers are available. So thank you all so much for sitting on a little bit later than normal, and we'll see you next time.